right, welcome back. Today we're going to take a look at something called a hypogeometric distribution. And before we get there, I'm going to again just kind of bring us back to our last couple lessons on binomial distributions and waiting times. Now those two things had something in common. They both followed repeated Bernoulli trials, meaning that our trials that we did had to be identical, independent, and have only two outcomes, success and failure. Hypergeometric is kind of the opposite of that. So there's a phrase here that often comes up when you're talking about hypergeometric, and it's called without replacement. That is a key feature of these. I will explain what I mean by that in a minute. But when it comes to the repeated Bernoulli trials, hypergeometric are actually the opposites. They do not have identical experiments. They are not independent of each other, and they may have two outcomes, but they could have three or four or any number of outcomes as well. Whereas binomial kind of pretty much states you have to have two. I mean, the fact that it's called binomial suggests two. So just to kind of give you an idea of where this occurs, hypergeometric comes up when you're doing things. The most obvious example is where you're drawing cards from a deck. And the reason for that is when you draw a card from a deck, the next card you draw, it's not the same experiment, assuming that you're not replacing cards as you go. So for instance, that first card I draw, the very first card I draw, its probability of being an ace is 1 out of 13 or 4 out of 52, same difference. However, the probability of my second card being an ace, it's not the same experiment because I'm not drawing from 52 cards anymore. I'm drawing from 51. So that's changed. And it's not independent because it's either 4 out of 51 or 3 out of 51, but it depends on whether the first card I drew was an ace. So they're not independent trials. And in this case, there are kind of two outcomes. I get an ace or I don't. So that part doesn't matter, but they're not independent and they're not identical. Now, this same thing happens if I'm drawing people from a group of people, if I'm drawing marbles out of a bag and they're different colors. It comes up anytime I'm removing something without replacing it back in. So that's really where hypergeometrics come in. Now, there is an equation for it that I put right there. And rather than even look at that equation, if I could cover it up, I would, but putting my hand on the screen does nothing. There, I'm going to cover it up that way. We're not going to actually worry about memorizing that equation because it's kind of nasty. Now that said, as a mathematician teacher, I should at least show you the equation. Already feeling guilty about my choices. Okay, and I want to point out that despite the fact that that notation looks kind of brutal, we have used that equation before. We have solved problems with this. Let's jump into an example and you'll see exactly what I mean by it. And I'm not even going to refer back to the equation as I'm solving this example. Example 1. What is the probability you'll get 2 aces if you're dealt a hand with 5 cards? So here's what we're going to do. When it comes to these, I'm going to kind of make a shopping list. My shopping list is I want 2 aces. Now, technically, I'm drawing 5 cards. I'm not going to write down 3 others. I think it's kind of assumed that if I'm looking for 2 aces, I'm looking for 3 other cards. So I don't have to complete that part of the shopping list, but I'm going to write down that I want 2 aces. And without referring back to the equation, we did questions like this already. How many ways can I get 2 aces in a hand of 5 cards? Well, there's 4 aces and I want 2 of them. And there's 48 non-aces and I want 3 of them. And then what's the way of selecting 5 cards in general? Well, that's just 52 choose 5. So we actually have solved questions like this. We may have solved this exact question back in the last unit. All we're doing today is really putting a name to it and kind of formalizing it. Now that I've written it like that, I'm going to show you that equation again and see if you can kind of make the connection that that's really the same thing. The A is the number of things that I'm shopping for. There's 4 aces. 2 is the number of them I want. The B is the rest of the stuff. That's the 48. The n minus x is the 5 things minus the 2 I've gotten that I wanted specifically to be aces. That's 3. And on the bottom, the a plus b is the total number of cards, aces and non-aces. And the 5, the n, is the total number of cards I'm selecting. So you don't have to worry about using that equation if you understand how it works. Again, basically just using stuff from last unit. I guess I should finish off the problem by actually calculating that in my calculator. So 4 choose 2 times 48 choose 3 divided by 52 choose 5. And that works out to 0.0399 or about 4.0%. Very, very close to being exactly 4.0. So there's a 4% chance. Wait a second, that seems kind of high. Let me just double check that. Yeah, I did it again. It's still 4%. Okay, so even though I was wrong about being wrong, so I'm trying to make sure my brain gets that statement correct. I was wrong about being wrong. I do want to point out that there's nothing wrong with double checking your work if something looks suspicious. You're better to double check it and find out that your answer was right than to not check it and find out your answer was wrong. So I was thinking that seems very high because there's a whole bunch of different pairs I could get. But what this doesn't take into account is I could get a pair of threes with a pair of aces, or a three of a kind fives with a pair of aces, or a whole bunch of other things with a pair of aces. So yeah, I guess 4% isn't that unreasonable. But yeah, if your spider sense is ever tingling, that's how I refer to it. Something just looks a little wrong. Feel free to double check it. It could be that I punched something wrong into my calculator. Double checking it never hurts. Example 2. A bag contains 8 blue marbles and 12 red marbles. What is the probability that you'll get at least 2 blues if you pick 5 marbles out of the bag at random? Before we do this, I just want to again kind of reiterate why this is hypergeometric. The first marble I draw out, if we say 2 blues, we're looking for 2 blues. Well, the probability of drawing a blue on my first marble is 8 out of 20. The probability of drawing a blue on my second marble is either 8 or 7 out of 19. So the fact that it's out of 19 means it's not an identical experiment to the first one, to the first drawing of a marble, and it's dependent on the first marble being blue or red. So that's what makes this hypergeometric, is that we're drawing without replacement, and it changes the experiment each time. So what is the probability that we get at least 2 blues if we pick 5 out of the bag? So probability that blue is greater than or equal to 2. And as soon as I see greater, or at least in this case, or at most, or any of those words, it tells me that I'm going to have to probably look at a couple of cases. So again, I can think about this and do it directly, and I could do the probability of drawing 2, 3, 4, or 5 blue marbles, which is 4 things to calculate. Or I can say the only things I don't want are 0 or 1 marble, blue marble. And I think I'm going to approach it that way. So I'll do it as 100% minus the probability of getting 0 blue minus the probability of getting 1 blue. Okay, so now I have 2 hypergeometric equations to solve, which at least is a little bit prettier. Okay, so for 0 blue marbles, I have 8 blue, I'm going to choose 0, 12 red, I'll choose 5, out of 20 marbles, of which I'm choosing 5. Or 8 choose 1, 12 choose 4, out of 20 choose 5. So even though that those are 2 separate equations, I think you'll notice that even if you have to do a few of them, there's a very easy pattern to follow there for making up those equations. I'm not always referring back to the equation, I'm just thinking about what it is I'm doing. All right, so let me calculate those as percentages. 8 choose 0 does nothing, so that's just 12 choose 5 out of 20 choose 5. And that gives me 5.1%. Makes sense. It would be pretty difficult to get no blue marbles if I'm choosing 5 of them. And the bag's almost half blue. And then the next one is 8 times 12 choose 4 over 20 choose 5. And that one's 25.5%. Alrighty. Okay, so if I actually just do those subtractions, 100 minus 5.1 minus 25.5 gives us 69.4% chance. So there's a 69.4% chance that I'll get at least 2 blue marbles if I draw them from the bag. Okay, so not too painful. The equation's actually pretty straightforward. Okay, I'm going to point out that we can extend our hypergeometric distribution, unlike our binomial, at least not easily, to do 3 or more outcomes. And this is where the whole idea of a shopping list comes in really nice. So a hockey team has 3 goalies, 5 defensemen, and 8 forwards. And by the way, if your knowledge of hockey is about as good as mine, don't worry about it. I'll walk you through. Uh, what is the probability that if 6 players are chosen at random, you'll get 1 goalie, 2 defensemen, and 3 forwards to make a starting line? So that's actually what goes out on the ice to play is 1 goalie, 2 defense, and 3 forwards. And I'm saying, what is the probability you'll actually get that if I just walk into the locker room and randomly say, hey, you 6, go hit the ice, without any knowledge of who's playing what position? This, by the way, is loosely based on my brief career as a rugby coach. I coached girls rugby for 2 years. I still don't know how many players are supposed to be on the field at one time or the names of any of the positions or what they do. They hit each other. I got that part. That's all I got. Luckily, I had a few students who really knew what they were doing and kind of led everything. I just kind of brought them water. Anyway, so this one, if I write out the generic version of this equation, like the equation at the beginning, the nasty looking one, it's horrific looking. But this one's actually pretty easy to extend if you think about how it's made. So I'm going to start down by basically making my shopping list. I'm looking for the probability of getting 1 goalie, 2 defense, and 3 forwards. So that's the proper way to write that out. And then I just say, of my 3 goalies, I'm choosing 1. Of my 5 defense, I'm choosing 2. Of my 8 forwards, I'm choosing 3. So that's getting what I want, which is an actual functional hockey team, divided by the number of ways of selecting 6 people at random. There are a grand total of 16 players, and I'm choosing 6 to go play. So that would be the bottom number. So is this that much harder than the 2 possible outcome version? Like just 2 things? Not really. Just 1 extra factor on the top. So make the shopping list. Now find out what the probability is I get that shopping list. So on the top, I have 3 times 5 choose 2 times 8 choose 3 divided by 16 choose 6, and I'm getting out 0.2097, which is actually going to round off to 0.210 or 21.0%. Okay, so it's about a 1 in 5 chance that if I randomly select 6 players in the locker room, I'll actually have a functional team. That's not too bad, I guess. It's not fantastic, but it's still better than anything I ever did coaching rugby. Okay, how about expected values for this stuff? So the actual equation that most books use is this one, but I want to point out that if you understand that A is the things you want and B is the things you don't, A over A plus B is really just the probability of getting A. And that's how we're going to simplify it, is that we're going to just use this equation right here, which you might actually recognize as familiar because it's the same one that worked for binomial distributions. It actually isn't really that shocking that that one works if you think about what it means. All this is saying is that, well, in this example, example 4, we have a bag containing blue, red, yellow, green marbles. It's just saying if a quarter of the marbles are red and I choose a bunch of marbles, I'm expecting a quarter of the ones I choose to be red. That's all that equation says, n times p. So in this particular example, we do have the 2 blue, 4 red, 6 yellow, and 8 green marbles, and we're going to choose 5 marbles at random. and we want to know the expected number of each marble that we'll get. So the expected number of blue marbles should be equal to the number of trials, we're drawing 5 marbles, times the probability of getting a blue marble. The blue marble, there's 2 of them, and there's 20 marbles in total. So 2 out of 20 gives us, times 5 is 10 out of 20, or 0.5. And just one final reminder, because I see it on tests all the time, a bunch of people will convert that to 50%. That's not the answer to the question. I'm not saying 50% marbles. I'm saying there are 0.5 blue marbles. This is not a probability. Don't convert to a percent. For some reason in this unit, everyone who sees a decimal number less than 1 tries to convert it to a percentage. And then I can do the same thing for the number of red marbles. There's 5 marbles being chosen. The probability of being red is 4 out of 20. That's just 1. That doesn't mean there's 100% certainty of getting red marble. It means that on average you'll get 1 red marble. Expected number of yellow is 5 times 6 out of 20, which is 1.5. And expected number of green marbles is 5 times 8 out of 20, which is 2. So just to be clear, of your 5 marbles that you chose, you'd expect on average to get half a blue marble, 1 red, 1.5 yellow, and 2 green, despite the fact that 2 of those are not possible answers. It's just saying that if you did it a million times and divided it out, that's what you would get. Let's just try a couple more examples, get the handle on this, and I think you'll see it's not actually that tricky. 20 hamsters are for sale at a pet store. 12 of them are brown. You randomly bought 5 of the hamsters, just in case you want 5 hamsters. What is the probability that at least 2 of them are brown? So we're looking for the probability that we have 2 or more brown. Brown is greater than or equal to 2. Again, with 5 hamsters, we could do the probability of 2, 3, 4, and 5 and do 4 calculations. Or we can say that's equal to 100% minus the probability of 0 brown minus the probability of 1 brown. Okay, so 0 brown. 12 of them are brown, so we have 12 choose 0, and 8 non-brown, we're going to choose 5 of those. And on the bottom, there are 20, and we're going to choose 5 total. This one we just change a little bit. 12 choose 1, 8 choose 4, over 20 choose 5. And now we can punch that into our calculator. 12 choose 0 is 1. 8 choose 5 divided by 20 choose 5. Oop, that's actually pretty small. 0.36%. I'm only doing 1 decimal place on these, so I'm just going to do 0.4%. It's also the very unlikely outcome. Since most of them are brown, it's very unlikely you're going to get no browns. This probability should be higher of getting 1. It is more likely. So that's just going to be 12 times 8 choose 4 divided by 20 choose 5. And that's 5.4%. So if I put those together, that's 94.2%. So there's a pretty good chance you're going to get at least, yeah, 90% or 94.2%. We're going to get at least 2. I was thinking, we didn't calculate the 2, but we don't need to. We only have to get rid of the 0 and 1, and then we're left with 2 or more. So a very decent probability we'll get at least 2 brown hamsters. What is the expected number of brown hamsters that you'd get? Well, you're doing 5 trials. You're selecting 5 hamsters. The probability of getting a brown hamster is 12 out of 20. And 5 times 12 is 60, divided by 20 is exactly 3. So I'd expect that of my 5 randomly selected hamsters, on average, 3 of them would be brown. Makes sense. 60% of the hamsters are brown, so 60% of my 5 should be brown. A bridge hand of 13 cards is dealt to you. Now, I always think this is funny because I'll have students that put up their hands and say they don't know how to play bridge. I don't know why you need to know how to play bridge to answer this question, but let's go with it. A bridge hand has 13 cards dealt to you. What is the probability you'll get 6 spades, 4 hearts, 2 diamonds, and a club? That is a pretty specific hand. I mean, it doesn't say which 6 spades, but it's still like that's a pretty prescribed hand. So let's start off by making our shopping list. The probability that we get 6 spades, 4 hearts, 2 diamonds, and 1 club. By the way, this is why the generic notation is so difficult to write out. When you write it like this, it's pretty obvious what it means, but writing that out with all generic variables is crazy. That's just going to be 13 spades, choose 6, 13 hearts, choose 4, 13 diamonds, choose 2, 13 clubs, choose 1. Out of 52 cards, choose 13. Okay, and the hardest part of this one, honestly, is getting it right in your calculator. So rather than waste your time, I'm just going to pause on this one and I'll come back when I've got the answer. Okay, and while I'm not absolutely positive I'm correct, I'm hoping it's 0.196%. Again, it's a pretty low percentage, which always makes me a little suspicious because it's hard to tell low versus very low with things like this. But again, I can say that that is a very specific hand that you're getting. I'm getting that correct number of each suit. Seems like a fairly unlikely thing. So I'm not too shocked that the number's that low. It may be wrong, but at least it's reasonable. Hopefully it's actually not wrong. What is the expected number of each suit that we get? Okay, so the expected number of spades is just 13 trials times the probability of getting a spade, or the probability of drawing a spade as one single card, which is 1 out of 4. And 13 divided by 4 is 3.25. Now, I'm not going to bother calculating the others. Any suit is going to be 3.25 because honestly, there's the exact same calculation for all of them. There's 13 of each suit, and there's 1/4 chance of getting any given suit. And I mean, it makes sense. Again, if the deck or the cards are made up of 1/4 of each suit, you'd expect that 1/4 of your 13 cards are going to be each suit. Impossible to get on any single hand, but on average, what you would expect to get. Okay, the last thing that I want to do today, and I really want to drive this home because this is an important idea for solving actually most real world problems. And that's approximating hypergeometric distributions using binomial distributions, despite the fact that I've tried to drive home that these are drastically different things. Binomial needed to be the repeated Bernoulli trials. Hypergeometric is definitely not the repeated Bernoulli trials. Yet we actually can make an approximation. Let's do the math first, and then I'll try to explain why this works. You'll probably figure it out on your own, and that's actually probably better for understanding it. But if you don't get it on your own, I will help you through it once we've done this one. Okay, so a bag of marbles contains red and blue marbles in equal numbers. What is the probability of getting all 3 red when the total number of marbles in the bag is 10, and then a whole bunch of other variations? So if there's 10 marbles in the bag, what's the probability that I'll draw 3 red ones, knowing that half of them, 5 of them are red and 5 of them are blue? So probability that there are 3 reds is going to be 5 choose 3. So there's 3 reds. And then 5 blue choose 0. And on the bottom, we have 10 marbles choose 3. So 5 choose 3. The 5 choose 0 does nothing. Divide by 10 choose 3. And I get 8.33%. And these ones, actually, you know what? I think I'm going to keep 3 decimals on these just to show you something interesting. Okay, the next one. If you're okay with this, I think I'm going to skip out some of the notation just because it takes up a fair bit of space and I want to do this in very little space. I'm not going to write out the probability red equals 3 equals each time because that's the same for all of these. So I'm just going to jump to in this case, instead of 5 red choose 3, 5 blue choose 0, I'm going to do 50 red choose 3. And actually, you know what? I'm not even going to write down the 50 choose 0 because the choosing blue part is always going to be 1 anyway. 5 choose 0, 50 choose 0, 500 choose 0. It doesn't matter what it is. It's 1. So it just becomes 50 choose 3 over 100 choose 3. So 50 choose 3 divided by 100 choose 3. And I get 12.121%. Okay. This one over here is going to be 500 choose 3 over 1,000 choose 3. And when I punch that in, I get 12.462%. When I do it with 10,000 marbles, it's going to be 5,000 choose 3 over 10,000 choose 3. 5,000 choose 3 divided by 10,000 choose 3. And it is 12.496%. And when I do it with 100,000 marbles, it's going to be 50,000 choose 3 over 100,000 choose 3. Hopefully I punched that in correctly. And I get 12 point, and I'm even going to keep 1 extra decimal place this time just to kind of drive home an idea here. In fact, I'll write down all the decimal places I've got on this one. So I want you to look at those numbers and see what happens as the number of marbles in the bag gets larger and larger and larger. So with 10 marbles, it was 8.3%, but by the time I got to 100, it went up to 12.121. And by the time I went to 100,000, it went up to 12.499,625. Just make a prediction in your head. What do you think is going to happen if I went up to 1,000,000 marbles or 1,000,000,000 marbles? And I think you're probably going to get that it's going to actually kind of get closer and closer to 12.5. These seem to keep getting closer to 12.5. But why is that true? Well, I want you to think about it this way. If you had a bag with 1,000,000,000 marbles in it, 1,000,000,000 marbles in it, and it is a binomial, it is a geometric situation. The first marble I pick out is either red or blue, 50-50 chance. And the second marble I'm picking out, there's 1 less marble in the bag. And it depends on whether it was a red or blue for the first marble, whether or not the second one will be red or blue, the number that are left. So it is not identical because there's 1 less marble in the second choosing, and it's not independent because it does matter what the first marble was. However, with 1,000,000,000 marbles, is drawing from 1,000,000,000 marbles and drawing from 999,999,999 that much different? Those are almost identical experiments. They're very, very close to being identical. And when you're talking about a billion marbles, does it really matter whether the one missing was red or blue? Will that really change the probability of the next one? It's almost a 50-50. So despite the fact that these are not identical and not independent, they're extremely close to being identical and extremely close to being independent. And that's why we're getting these numbers that are very, very close to each other. So if we did this using a binomial distribution, we pretend it's binomial. The probability that red would equal 3, if we're drawing 3 marbles, would be 3 choose 3. Probability of success, which is 1/2 to the exponent 3. Probability of failure, which is 1/2 to the exponent 0. And then we just plug that into our, well, the first and last factor don't do anything. The middle part is 1/2 cubed, which is 1/8. 1/8 is 12.5%. 12.5%. Well, that's what we said this was approaching up here. That seemed a lot easier to calculate it that way. Before I do any of the others, where did the 10 marbles come into play? The 3 choose 3 was the number of selections, the number of marbles I took out of the bag, and the bottom 3 was the number of reds I wanted. The 1/2 and the 1/2 are the probability of being red and blue. It's independent of the number of marbles. And the 3 and the 0 are the number of reds and the number of blues. So it turns out that these are all the same. It doesn't matter how many marbles are in the bag, as long as half of them are red and half of them are blue. The binomial equivalent of the hypergeometric is going to be 12.5%. Okay. Now, since we did know the number of marbles in the bag, we didn't have to do all of the different calculations for the different number of marbles in the bag. We just needed to do it for one of them. So if there were 100 marbles in the bag, for instance, this is the right answer. So is that really any harder or easier than this? And I would argue that those are about the same level of difficulty. Possibly the hypergeometric is even a little bit nicer. So the question then is, why use an approximation when the correct way of doing it is easier or shorter? So why do we want to approximate the hypergeometric with our binomial? So let's do one more example, and then hopefully this will drive home why this is true. Let's say we want to choose 100 marbles from a bag of 100,000, half red and half blue. So just to be clear, the only difference between this one and the last version we did right there is that instead of choosing 3 marbles, I'm choosing 100 marbles. It's the only difference. Now, I do want to point out that even at 100 marbles, we're talking about 0.1% of the marbles being taken out. So the binomial approximation of this should be pretty good, because we're talking about taking out a very small number of marbles, which means that the experiments are almost identical and almost independent. Not quite, but close. Okay, so if we take out 100 marbles, I want to know what the probability is that I get 50 of each. Okay, so here's my shopping list. Sorry. We're going to start by doing it the binomial method to begin with, and then we'll do the hypergeometric after that. So the binomial geometric. Now, I guess I can write down. I'll just write down probability that red equals 50. I don't have to put down the blue equals 50. It's insinuated with binomial distribution, since there are only 2 possible outcomes. And this one says that it's going to be, there's 100 marbles being selected, and I choose which 50 of them will be red. And then there's the probability of being red to the exponent 50. and the probability of being blue to the exponent 50. Okay, that's how binomial worked. Okay, so pull out the calculator, 100, choose 50. Oh, I don't know about your calculator. You should actually try this if you're not doing it with me. Try that. When I punch into my calculator, there's actually like a pause where my screen goes blank for a moment um, before it comes up with a calculation. And then it comes out to be just over 1 times 10 to the exponent 29. Okay, and then I'm really multiplying by 1/2 to the exponent 100 because those are two things with the same base, so I should add the exponents. Or I'm just going to divide by 2 to the exponent 100. Okay, and I get 0.0795, which is, and I'm going to keep extra decimals here just so you can see it. That works out to be 7.9589237%. Okay, so that's my approximation. Let's do this the proper way using the hypergeometric distribution and see why we might like the binomial approximation. So this is the probability of getting 50 red and 50 blue, just so that we're consistent with the notation we use for hypergeometric, our shopping list. Again, really writing down red equals 50 is enough information. But for our hypergeometric, what we're saying is with 100,000 marbles, we want 50,000 marbles, choose 50. And then 50,000 blue marbles, choose 50, over 100,000 marbles, choose 100. Okay, so I pull out my calculator, 50,000, choose 50. Okay, my calculator went dead for about 3 seconds and then just came up with an error. And the reason for that is that number is ridiculously huge. Like ridiculously huge. Because it's 50,000 times 49,999 times 49,998, and it keeps going till I've chosen 50 numbers. And since each of those numbers is contributing at least 10 to the power of 4, my answer for this is going to be something in the ballpark of like 10 to the 4, or 10 to the couple hundred, 10 to the 200. And most calculators can only hold up to 10 to the 100. Okay, so calculator broke. And given that, I think you may now understand why we want to use our binomial distribution approximation instead of an actual geometric distribution. And I thought I'd just share for the record, I tried doing this in both Excel and Desmos, which are both pretty powerful online calculators, and neither of them can do the hypergeometric version of this. They both go wonky. Excel can't hold that many or that high a power. I tried doing it like manually to work around it, no luck. And Desmos just says undefined. It can't calculate numbers that are that large. So when it comes right down to it, in some cases, it's not a matter of which one do we want to do, it's which one can we possibly do. So if you ever get an error with a hypergeometric because the numbers are too large, you may have to attempt a binomial approximation, even if you know it's not exactly right. But in many cases, like in this one, I don't know. I'm looking up here and I'm saying if the correct answer is 12.5% and we approximate that with 12.499625%, I think we're doing pretty good. So I'll let you try some of these. I don't think you need to, yeah, if you're going to do any approximations of hypergeometric with binomial, make sure the question actually asks you to do that. I'm not going to put any weird ones in there that you have to do it. Or well, if you try and you get an error, then yeah, go back and try the binomial. But don't just jump to binomial every time. You should always try to do it hypergeometrically first. Okay, I'm going to stop there and we'll catch up with you in the next lesson where we're going to come back to some more binomial related stuff. See you later.